FLUX-3 generated this video, including the sound. Watch closely and listen. Now freeze just before this finger touches a key. Which key will it press? From this single frame, we know where the finger is, but not where it is going. The earlier frames reveal its direction and narrow the possible keys. The audio lets us test whether the video stays consistent. When the finger appears to press a key, we should hear the note that key would produce. So how can FLUX-3 keep the finger's movement, the key, and the sound consistent? To keep the finger, the key, and the sound consistent, FLUX-3 has to relate three kinds of information. The image shows where the finger and the keys are. The sequence of frames shows which way the finger is moving. The audio tells us what sound occurs as the finger reaches the keyboard. For the video to stay consistent, the finger should move toward one key, that same key should appear to go down, and we should hear its note when the finger appears to press it. Now change one thing. Have the hand press the neighboring key instead. The finger should follow a different path, a different key should go down, and we should hear a different note. We call what the hand does the action. Here, that action is pressing one key rather than another. At this point, we are connecting four kinds of information: what the scene looks like, how it changes, what it sounds like, and what the hand does. A model that learns from several kinds of information is called multimodal. FLUX-3 processes image, video, and audio through the same central part of its network. Because this part is shared, it is called the shared backbone. For the robotics research, a separate smaller network uses information from the backbone to predict what the robot should do next. This smaller network is called the action decoder. So before we ask how FLUX-3 can predict an action, we need to understand what its shared backbone learns during training. To understand what the shared backbone learns during training, start with one clean image and a random noise pattern of the same size. Choose a mixing level. At 50%, average every value in the clean image with the corresponding noise value. This produces a partly noisy image. At 1 pixel, for example, a noise value of 0.2 and a clean value of 0.8 produce a halfway value of 0.5. The full change from noise toward clean is positive 0.6. The network receives the partly noisy image and its mixing level. It does not receive the clean image or noise pattern as inputs. It predicts one change for every value. We compare those predictions with the correct changes to calculate the training loss. Backpropagation and the optimizer then update the network's weights. Repeating this with many images, noise patterns, and mixing levels teaches the network how a partly noisy input should change toward a clean image. To generate a new image, start with fresh noise. Predict a change, apply a small part of it, and give the updated input back to the network. Repeating these steps gradually transforms the noise into a new image. Together, these predicted changes describe a flow from noise toward clean data. Training the predictions to match the correct changes is called flow matching. FLUX-3 applies the same process to video and audio. Our piano clip contains 121 frames together with sound. Processing every pixel and audio sample directly would be expensive, so input encoders compress them into smaller sets of numbers that retain the information needed to reconstruct them. These compressed representations are called latents. The shared backbone performs flow matching on these latents. Output decoders then convert the final latents back into visible frames and audible sound. Black Forest Labs has not disclosed the exact production encoders, codecs, or decoders. But this training task has a weakness. A small region may be corrected using nearby details alone. The network can therefore succeed without learning how that region depends on the rest of the video. Consider this noisy region on the white key. The network can correct it while ignoring the finger above it because the nearby pixels already show a pale surface with two parallel edges. Extending those patterns produces a plausible key and lowers the training loss even if it removes part of the finger. The network can therefore succeed without learning the relationship between the hand and the piano. To make this local solution unreliable, give different parts of the same example, different amounts of noise. Leave some regions relatively clear and corrupt others much more strongly. If the contact between the finger and the key is heavily corrupted, the pixels immediately around it are no longer enough. The network must also use the wrist position, the pattern of black keys, and nearby video frames to determine what belongs there. Each amount of noise corresponds to a position between clean data and random noise. That position is called a time step. Using two different noise levels during this training process is called Dual-Timestep Scheduling. Here, time step describes how noisy the data is. It does not refer to a moment in the video. There is one more part. Create a second copy of the network. The main network receives the more difficult, noisier input. The second copy receives a cleaner version of the same example. At corresponding locations, train the main network's internal features to match the features produced from the cleaner input. This gives the main network a target containing more reliable information about the finger, the key, and their contact. The second copy is not trained independently. Its weights are updated as a slow-moving average of the main network's weights. This keeps its target features stable without requiring external labels or a separately trained teacher. The combination of flow matching the two noise levels and this feature matching target is called self-flow. Self-flow is intended to make the backbone use information from across the example instead of relying only on nearby details. If that works, a model trained with self-flow should generate better images, video, and audio than one trained with ordinary flow matching. Do the experiments show that improvement? In the controlled experiments, the answer was yes, although the improvement was modest. For video, the researchers used a score that compares a collection of generated clips with a collection of real clips. A lower score means the two collections are more similar according to this test. Standard flow matching scored 50.95. Self-flow reduced the score to 47.81. The image and audio experiments also showed smaller improvements. Those improvements remained when the research model was trained jointly on images, video, and audio. These results came from controlled research models. They do not directly measure how much self-flow improves the production version of FLUX-3. Black Forest Labs says it used this training approach when building FLUX-3 at a much larger scale. Its shared backbone is trained jointly on images, video, and audio from the beginning. The public video system can generate clips up to 20 seconds long with synchronized sound. This does not mean every output comes directly from the shared backbone. To produce full HD video, the system uses an additional upsampler that increases the resolution. Robot control also uses a separate output component. The shared backbone processes the robot's observations and produces internal features. A small action decoder reads those features and predicts the robot's next action, such as how its arm or gripper should move. This gives us a concrete test of the features learned by the backbone. If the action decoder can make accurate predictions from those features, then they preserve information that is useful for controlling the robot. Do the experiments show that they do? The robot experiments suggest that they do. The shared backbone processes the images observed by the robot. At several intermediate layers, it produces features describing what it sees. In the system called FLUX-mimic, a small action decoder reads those features and predicts how the robot should move its arm and gripper. This means the backbone is not directly controlling the robot. It produces features from the robot's visual observations, and the action decoder converts those features into movement commands. The researchers trained this action decoder while continuing to train the backbone for video generation. Early in that joint training, the ratings for generated videos fell by as much as 10%. Learning to predict robot actions had initially made the backbone worse at generating video, but the decline was temporary. By training step 3500, the video ratings had recovered, while the action decoder continued to predict robot movements from the backbone's features. This does not show that adding robot control has no cost. It shows that, in this experiment, the backbone adjusted to support both tasks without a lasting reduction in the measured video quality. Black Forest Labs and its research partners tested the system on factory tasks, including inserting components and manipulating flexible cables. These tasks require more than choosing one action from one image. After every movement, the robot receives a new observation and predicts another action. Suppose the robot tries to grasp an object and misses. Its next camera image shows that the object is still on the table. The system processes this new image, updates its action, and tries again. This repeated cycle of observing the result and choosing the next action is called closed-loop control. When FLUX-3 generates a video, it produces a possible sequence. It is not shown what happened in the real world and then asked to correct its output. A robot receives that feedback. Suppose it closes its gripper but misses the object. The next camera image shows the object still on the table. The backbone processes this new image, and the action decoder uses its features to choose another movement. The experiments show that these features can help the robot choose a new action after seeing the result of its previous one. They do not show that the backbone can take an action and predict what is likely to happen because of it. A model that can use the current situation and an action to predict the likely result is often called a world model. Does FLUX-3 actually have that ability? Black Forest Labs calls FLUX-3 a world model. Under the meaning used in its announcement, that description is reasonable. Give FLUX-3 the beginning of a video and it can generate a possible continuation with sound. To keep that continuation coherent, it must predict how the visible parts of the event are likely to change and which sounds are likely to occur with those changes. In the piano performance, the fingers, keys, and notes must continue together. Black Forest Labs uses the term world model for the learned representation that supports this kind of prediction. The action results provide additional evidence for this description. Black Forest Labs reports two approaches. One trains action prediction directly within FLUX-3. The other uses the FLUX-3 backbone in FLUX-mimic, where a separate action decoder reads its intermediate features and predicts how a robot should move. Together, these results show that the backbone can support image, video, and audio generation, as well as robot action prediction. That supports Black Forest Labs' use of world model in a predictive, generative sense. But a stronger test asks a different question. Give the model the current observation and a chosen action, then ask it to predict the consequence of that particular action. After that, keep the observation unchanged and change only the action. In the piano example, first ask, what will happen if this key is pressed? Then begin from the same observation and ask, what will happen if the neighboring key is pressed? The predicted finger movement, the key that moves, and the resulting sound should all change together. Details unrelated to the chosen action should remain unchanged. If a model can reliably make both predictions, it can simulate how a chosen action is likely to change the current situation. The public results we have discussed do not clearly demonstrate that FLUX-3 can perform this kind of general action condition simulation. So the most accurate answer is not simply yes or no. FLUX-3 is a world model in Black Forest Labs' predictive sense. Whether it can also serve as a general interactive simulator remains an open question. With that distinction in place, return to the generated performance where we began. Return to this generated piano performance. It brings the entire idea into one example. FLUX-3 begins with noise in a compact numerical representation. Its shared backbone repeatedly predicts how those numbers should change until they can be decoded into an image, a video, or synchronized sound. Self-flow trains the backbone to use information from across the example. When different regions contain different amounts of noise, nearby details are not always enough. To reconstruct the contact between the finger and the key, the backbone may need information from the hand, the keyboard, nearby frames, and the sound. The features learned through this process can also support robot action prediction. Black Forest Labs reports one approach that predicts actions within FLUX-3 itself. In FLUX-mimic, a separate action decoder reads the backbone's features and predicts how the robot should move. This is why Black Forest Labs calls FLUX-3 a world model. Its shared representation supports predictions across images, video, sound, and action. The open question is whether it can perform the stronger test we described. Starting from the same observation, can it predict how different chosen actions would produce different futures? The public results do not yet give us a clear answer. What they do show is an important step toward that goal. A single learned representation can connect what a system sees, how a scene changes, what it sounds like, and what an agent might do next.